Well, hello, this is Dr. Dave Gatros from Florida State University, Panama City campus in the Department of Computer Science. And what I want to do today is talk about binary addition, subtraction, overflow, and sign extensions. Pretty interesting topic. This has been requested by my students to explain the process a little bit more, so glad to do it. Glad to do it. Here we go. A little bit of background. First of all, to get the most out of this presentation, you need to understand binary numbers. You also need to understand how we represent negative numbers inside a computer using two's complement. And if you don't know that, this won't be enough to actually give you that background information. Go back to those videos, review that material, then come back to this one. Just to recap, negative numbers are represented by two's complement. Two's complement being the most prominent way to represent negative numbers inside computers today. Looking at the number on a signed integer number, you look at the leftmost bit. If the leftmost bit is 0, it's a positive number. If it's 1, it's a negative number, and it's represented in two's complement. I'll go over two's complement right now. Recall the rules for converting a positive number or a negative number to positive. It's the same. The first thing you do is you reverse the bits in the number, and then you add 1 to it. Now here's an example. We're going to use a 5-bit signed number. Signed number being the leftmost bit's the signed bit. Here is the number 10 in binary, represented by 01010. That's 10. That's a positive number. To convert it to a negative number in two's complement, we reverse all the bits. Then it becomes 10101. And then we add 1 to that number. And again, you need to understand binary addition. Subtraction inside a computer is accomplished by performing two's complement on the second operand and then actually performing a binary addition. So overflow is really detected the same way in both types. If the second operand is a negative number and a subtraction is converted to a positive, and if the second operand is a positive number, is converted to a negative number. Okay. A little bit more background for all of our examples in this presentation for the overflow. We're going to be using 5-bit numbers just to make it simple. Again, just to reiterate, the leftmost bit is the sign bit. You also need to understand the largest and smallest, or the largest number you can represent in both negative and positive numbers. The largest negative value we can represent in 5 bits is represented by the formula 2 to the n minus 1, where n is the number of bits. So for 5 bits, that's 2 to the 5 minus 1, which is 2 to the 4th, which is 16. Negative 16 is the largest negative number we can represent inside 5 bits. The largest positive value is actually one less than that. So that's represented by the formula 2 to the n minus 1, and then we subtract 1 from that quantity. And again, where n is the number of bits. So for positive numbers, it's 2 to the 5 minus 1, which is 2 to the 4th minus 1, which is 16 minus 1, which is actually the number 15. You're asking the question, why can you represent more negative numbers than positive numbers? Well, that's illustrated by this chart. On the left-hand side, we see a table that represents the 5-bit binary numbers, positive values, and on the right-hand side, we see the negative values. The left-hand side is just normal binary numbers. You just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 15. You'll notice the left-hand bit is 0, indicating it's a positive number. We convert the numbers to base 10 like we normally do. We just take the value of the column and add those together, the ones that have the 1 in it, and that gives us the number. Now on the right-hand side, you'll notice that the very top one, the first one, is negative 16. The way the two's complement work is that the leftmost bit actually takes on the negative value of that column. So the 5th position from the right is normally 16, 2 to the 4th. In this case, it takes on a negative 16. So when we go to the next one, we add 1 to that. So negative 16 plus 1, and that gives us negative 15. Negative 16 plus 2 is negative 14, and so on and so forth. Why can we have more negative numbers than positive numbers? Well, there's the same number of positions, but on the positive side, one of them has to be used to represent the number 0. 0 is not only considered a positive number inside the computer, it's also considered an even number, by the way. All right. But look at, before we go on, sign extension. We're using 5-bit numbers. but this is scalable to any size, 8, 10, 16, 32, 64, doesn't really matter. And the number remains the same. So in sign extension, we're using signed integer numbers. Whenever we extend the size of the number of bits, all we do is we take the sign and we replicate that. If it is a positive number, we replicate the zeros. If it's a negative number, we represent the one. We replicate the ones. Again, it doesn't change the value of the number itself. Okay, so addition. In binary addition, we really have 5 scenarios that we talk about. Adding two positive numbers and the results are positive, there's no overflow. When we're adding two negative numbers and the results are negative, there's no overflow. And we're adding a positive and a negative regardless of position, overflow can never occur. And that is because the number is going to be in between the two. So whenever you're looking at, let's say, two numbers, and you're looking at adding, if the signs are different, you can just automatically say there will never be overflow. Number 4, when you're adding two positive numbers and the results are negative, overflow occurs. It changes the sign. Likewise with adding two negative numbers and the results are positive, then overflow has occurred. Here is just some examples. I put the decimal values on the left hand side and the answer, and then using 5 bits I show how it is overflow or not overflow, and it corresponds to the different conditions. 7 plus 8 is 15. 15 is represented, it can be represented in 5 bits, and there's no overflow. Notice that we check the sign. And the way the machine does that is it looks at the sign bits of the two previous numbers, and if it's the same, in other words, if it's the same, if both values are the same and the results are the same, we're okay. Likewise in negatives, both signs are the same, the results are the same, we're okay. There's no overflow. Okay. Condition 3, we're adding a positive to a negative. Again, can't be overflow at all. It doesn't matter that the signs are changed, it's just that they're different. We're adding, on condition 4, we're adding two positive numbers together. Now 16 is a positive number, and you'll notice that when we add 8 and 8 we get 16. It actually turned it negative. This is actually a negative 16, so overflow occurred because the sign has changed. Likewise with this one, we're adding a negative to a negative. We get negative 19, and again we initially start out with two negative numbers, and we end up with a positive number in 5 bits. Now when you're doing this arithmetic, you'll notice that when you're doing the addition, sometimes like when we add these two ones together, it produces a 0 with a carry of 1. The 1 is actually discarded and not used in this context. Subtraction is slightly different, but remember it's essentially just an addition. The extra step we take is we take the second operand and we perform a 2's complement operation on it, and then we perform an addition. So essentially what's going to happen is once we do the 2's complement operation, it conforms to the addition overflow detection. Subtraction overflow cannot occur when the signs of the values are the same. And that's because whenever you do a 2's complement on the second operand, you're changing the sign essentially. Subtraction overflow can occur when we subtract a negative from a positive. It can also occur when we subtract a positive from a negative, and we make these two scenarios different. When subtracting, we perform the 2's complement on the second operation and add. Once the 2's complement operation is performed, we look at it as just as if it was a addition. We're going to break this up into 6 scenarios just because subtracting a positive from a negative and negative from a positive are really two different things. Condition 1, subtracting two positive numbers. Results will always be between the two numbers. It can't be overflow. Likewise, when we're subtracting two negative numbers, the results will always be between the two numbers. It can't be overflow. 3, when we're subtracting a positive from a negative, it's essentially adding two negative numbers. And if the result is a negative number, there's no overflow. But when we're subtracting a positive from a negative and it results in a positive number, then there is an overflow. And remember, that's because we're essentially adding two negative numbers. And if it's a positive, it changes the sign. 5 is just the opposite. Subtracting a negative from a positive number is essentially adding two positive numbers, and if the result is positive, we're okay. But if it's a negative, now we have a problem. Here is just a couple of conditions. The first one is we're taking 14 from 15. That should be the number 1. And you'll notice that the highlighted in red, that is the number 14 that we've converted into it's a positive number, and we converted into 2's complement and did the add. And you'll see that we come up with the correct answer. There's no overflow. Likewise, when we're doing the same thing with two negative numbers, I just took negative 15, and I should have actually had the minus sign inside there, and I'll correct that on the next go around. And again, no overflow. We didn't change the sign. That actually, the number right here is actually negative 1 in 2's complement. Now, condition 3 is negative 15 minus 1. Now, this is a positive from a negative. Overflow is possible, but in this case, it's not. It's not going to happen. It gives us the negative 15, which is well within the range of a 5-bit number. Negative 16 is actually what can occur. So there's no overflow here. You'll notice that when we convert the 1 to a negative 1, both signs are negative and the result is negative, and we're okay. Now, the next condition, we're actually negative 15 minus 4. So I take negative 15, I convert the 4 to a negative 4, and do the addition, and you'll notice that the sign has changed. This is an overflow condition. And 19, that tells us too, the largest number we know we can represent inside of 15-bit or 5 bits is negative 16, so we know that's going to overflow. Here is subtracting a negative from a positive. 12 is within the range of 5 bits. We know it's not going to overflow, but let's look at it. I take 2 and I convert it, negative 2, and I convert it into a positive 2, and do the addition with 10. That comes up with 12. The signs are the same. There is no overflow. Here we have 15, and we subtract a negative 4. It's a negative from a positive. I take the 4 and I convert it into a positive number and do the addition, and you'll notice I come up with 19 down here, but that leftmost bit is a 1. The signs have changed. Okay. A little bit a review. I'm not going to go into multiplication and division overflow just yet. That's another video, but I will be doing it, and I look forward to doing another for them. Love to do these requests. Give me more videos to do, and thank you very much for watching my channel.